Chapter 6, Part 4 video. This is the final section for Chapter 6, and we are getting to polar coordinates. Now, we introduced them a few classes ago, but this is where we'll formally define and do some practice with polar coordinates. So we are going to look at the polar coordinate system and look at converting between rectangular and polar coordinates. We're going to look at converting equations, and then we may or may not get to finding distance using polar coordinates. Why is this important? Use of polar coordinates sometimes simplifies complicated equations, and they're very useful in calculus and higher math. I'm not sure why that has a line break there, but it will be fixed in the copy of notes that are posted on Blackbaud. So let's start by defining the polar coordinate system. The polar coordinate system is a plane, and remember, a plane is like a piece of paper that never ends. It's flat, and it extends in all directions along a flat area, okay? It has a point called O, which we call the pole. Think about that as like the North Pole or the South Pole is the very tip of the Earth. Then the pole is the very center of our polar coordinate system. And then we have a ray that goes out from that pole, and you can think about that as like the positive x-axis. Okay, so that ray that comes out from the pole is called the polar axis, just like the x-axis, except this time we don't have an x and a y-axis. We're just doing everything in reference to this one ray. Then we can find any point on this plane by using polar coordinates using a radius or distance and an angle theta. And we're always going to measure theta from the polar axis, and we're going to measure counterclockwise just like we did in the rectangular coordinate plane. The initial side of our angle is always starting at the polar axis. So this is what we mean by initial, is where it starts, and then it rotates over to our terminal side. And remember, initial means start, terminal means end. Okay, so all of this, all it says is that we have a plane, and this time, instead of doing little rectangular boxes in X and Y, what we see on this plane is almost like concentric circles spinning out, because we're not measuring over and up, we're measuring out and around, a distance and an angle. Okay, so let's see if we can plot a few points. So I always think about this as standing at the origin, which we can now call the pole, and facing out along our polar axis or our positive x-axis. And then I'm going to walk a distance of 2, 1, 2, and then spin that radius around by pi over 3. Pi over 3 is 60 degrees, right? We know this from the unit circle. So on our graph here, that's a distance of pi over 3. So there would be my angle and my radius of 2. So my point is here on my polar coordinate plane. Okay, so I'm going to erase my work. I drew it so that we could visualize it, and what we're left with is that point on the plane. We're going to do it again for part B. And this time I'm going to show you what if I consider the angle and then the radius. And for me, it's easier to think about the angle first. So if we start with the angle, then we want to face the angle 3 pi over 4. 3 pi over 4 is in quadrant 2. It is our angle of 135 degrees. It's halfway between our pi over 6 and pi over 3 angles. So again, I start out facing my positive x-axis, and then I spin around until I'm facing my angle of 3 pi over 4. Okay, so this red line kind of represents the angle, 3 pi over 4. And then I'm going to go a distance of -1. Remember, a negative distance means I'm walking backwards. So if I'm facing out the ray that we just drew, the 3 pi over 4, and I take a step backwards, what I end up with is a point right here, still on the circle with a radius of 1, but I took a step backwards. So I'm in quadrant 4. Okay, So we end up with that red point there. And again, I'm going to go through and erase the previous work so that we can see just the solution. And we end up, the solution is just that point. Okay. We don't have to do this in radians. We can do it in degrees as well. This time I want to try a negative 45-degree angle. So facing out on our polar axis, rotating a negative 45 degrees means negative angle means I'm rotating clockwise. So now I'm rotating clockwise to 45 degrees. That's my ray. And then my point has a distance of 3. 3 means I'm going to walk along that ray 3 units. 1, 2, 3 units. And there's my point. So now I'm going to go through and erase my previous work so that I can see my answer is just that point. Now on your notes, I don't expect you to erase your previous work, but I want to make it clear that our answer is not a line segment or a ray or a vector. Our answer is still a point. When we're plotting a point, the answer is the point. However, we use that idea that we developed with vectors in order to find the point, the idea of a distance and an angle. Okay, so these are 3 examples of polar coordinates. We also did examples in class where we looked at a negative radius and a negative angle. We can have that. And the nice thing about polar coordinates is if you don't like having all of the negatives, we can always convert them to positive numbers because of our angles being coterminal. So when we're looking at our angles, how do we find the other points that represent, or the other ways that we can represent the same point? If we have a point on polar coordinates with r and theta, we can rename that point by finding coterminal angles of theta. That's what this first method says. We can rename it by using any coterminal point, meaning if I have a negative angle, all I have to do is add 1 rotation. If it's in degrees, that would be theta plus 360 degrees. And then we can make any negative angle become a positive angle just by naming it by one of its coterminal angles. And then if we have a negative radius, we can make it positive, so we can do the opposite of that radius. The only thing is we have to add not 1 full rotation, but a half rotation, so pi, right? Just like when we were finding our solutions to trigonometric functions, the 2 points that are directly across from each other are pi radians away from each other. So if I'm going to negate my radius, if I'm going to turn around, so to speak, then I need to also change my angle by half of a rotation. So we can think about this as theta plus 360 degrees. So we're still doing all the coterminal angles, but then also plus half of a rotation so that I'm facing the opposite direction. That way, instead of walking backwards, I can walk forwards. Okay, we will be practicing this in class as well. So let's take a look at how do we convert. If we have our point in polar coordinates and I want to write it into rectangular coordinates or vice versa, we have this system set up. Now, just like we saw with vectors, if I have a point giving an x and a y, I can call that point xy. That's what we saw with vectors. But we also said, well, that's a dilation of the unit circle. And since the unit circle had cosine of theta, comma, sine of theta, our new point can be written as a dilation of that, multiplying it by our radius or our magnitude. So the point then becomes r cosine of theta, comma, r sine of theta. We developed that during our introduction to the chapter. That class recording is posted in the class recordings folder, and the slides are also posted on the topics page. So if you wanted to review that in more detail, I would go back to the class recording. But that's where these equations come from. We know that x is r times cosine of theta and y is r times sine of theta. We also know from our little triangle here, we can use the Pythagorean theorem to say that r squared is x squared plus y squared. And that's the exact same way when we were looking at trigonometric functions that we got that cosine squared plus sine squared equaled for the unit circle 1. For now that we're not only using points on the unit circle, this would be r squared, right? Our radius. So sine squared plus cosine squared equals our radius squared. That's the Pythagorean theorem. And our definition for tangent has not changed, but sometimes we will need to use tangent. So we have a definition for sine and cosine in order to convert. We also need a definition for tangent. This is the same definition for tangent that we have been using. It's y over x, and we can also think about that as sine of theta over cosine of theta. So the definition for tangent didn't change. We're actually not changing any of our rules here. We're just now going to apply them in a new context, in the context of polar coordinates. So let's take a look at an example. In this example, we are given polar coordinates and we want to find the rectangular coordinates. So I know that this is r and this is theta, and I want to find x and y. So somehow I want to convert from r and theta into x and y. Well, we have those two equations, the first two equations on the last slide. X equals r times cosine of theta, and y equals r times sine of theta. So substituting our values, r is 2, cosine of theta is 7 pi over 6. That's 2. Cosine of 7 pi over 6, if I look at that on the unit circle, 7 pi over 6 is here. Cosine is square root of 3 over 2. Multiplying those across, I get the square root of 3. Do the same thing for y, 2 times sine of 7 pi over 6. Our y value here is 1/2. So I know this is 2 times 1/2, which is 1. So our rectangular coordinates are square root of 3, 1. That's converting from polar to rectangular. Okay, and when we're doing that, pretty straightforward, we can substitute into our two formulas to find x and y. Okay, for our next example, we're going to convert instead of from polar to rectangular. Now we're converting from rectangular, our given is rectangular, and we want to find polar coordinates. And for polar coordinates, remember there are an infinite number of ways we can write it. So we just need to find 2. That's our challenge. So the first thing that we want to do, we're given x and y, and we need to find r and theta. R and theta. That's what we need. So the first thing I'm going to notice is that I have x and y, I need r. I can use that Pythagorean identity. R squared equals x squared plus y squared. Then r equals the square root of x, which is 1 squared, plus y is -1 squared. That's the square root of 1 plus 1, or the square root of 2. We've got r. Now we need theta. So there's a couple ways we can do this. We do know that x equals r cosine of theta. So that's one way we can do it. We can also use y equals r sine of theta, or we can use tangent of theta equals y over x. Okay, now we're given x and y, and we need theta. So the most straightforward, based on the already given information, is tangent. However, now that we have r, we can use x or y as well if we're more comfortable with sine or cosine. I think for the most part, we tend to be more comfortable with sine and cosine. So I'm going to go ahead and show you using x equals r cosine of theta. So we say x equals r is the square root of 2 cosine of theta, and x is 1 equals the square root of 2 cosine of theta. Then cosine of theta equals 1 divided by the square root of 2, or the square root of 2 over 2. Theta, you can use cosine inverse. I'm going to use the unit circle. Where does cosine equal square root of 2 over 2? We have two angles here. where cosine is the square root of 2 over 2. That's pi over 4 and 7 pi over 4. Okay, now it's not that we get to choose which of those angles. We now have to look back at our rectangular coordinates, right? Because this is what we're looking for. We're looking for the angle to these rectangular coordinates. So the point 1, -1 is going to be here in quadrant 4. So that means the angle that we're looking at is 7 pi over 4. So theta is 7 pi over 4. So we now have our polar coordinates, square root of 2 comma 7 pi over 4. We want to write this one more way. So what we can do is we can add or subtract to find a coterminal angle. I'm going to make it our negative angle. So that would be pi over 4 in the clockwise direction. That makes this square root of 2 comma negative pi over 4. So we have two coordinates here. You could find a different one. There are an infinite number of points that you could write for this question, but as long as you find 2 of them, that's what we're looking for. Sometimes I will ask you specifically to find one with a negative radius. Sometimes I will ask you to specifically find one with a negative angle. So we should be familiar and comfortable doing all of those things. If I wanted to do this same question with a negative radius, then I would say, okay, a negative radius means I need my angle to go the opposite way. I need to flip the ray 180 degrees. So now my angle here, the angle that matches my pi over 4 reference angle, is going to be 3 pi over 4. So I could also do negative square root of 2 comma 3 pi over 4. Okay, I'm not going to keep going. I could keep going on this same question for as long as we have, but I want to make sure that you see we can write the same point in so many different ways for polar coordinates. Okay, in our next example, we are converting not just a point, but an entire equation. So in this case, I'm given the equation in polar coordinates. Notice it has an r and a theta, so this is a polar equation, and we want to write it in rectangular form. So that means I want to turn this equation into just x's and y's. Now I can start substituting, just start substituting for r, start substituting for sine or cosine or tangent, but what we really should do, just like we were seeing in the last chapter, is do a little bit of setup. So if I know that r equals -2 cosecant theta, then I can divide both sides by cosecant theta. We didn't have any identities with cosecant. So if I divide by cosecant of theta, now I can reciprocate that. And the reciprocal of cosecant is sine. So this becomes r sine of theta equals 2. That makes us happy because we know an identity for r sine of theta for polar coordinates. R times sine of theta is y. Y equals, I drop my negative, -2. So that's the equation in rectangular form. To confirm this on the calculator, I'm going to show you in class. The trick is we need to change our mode. We saw function, that's what we've been using so far. In the last section, we saw parametric mode. This is now polar mode. And when you go into the y equals menu, it will let you write your equation with theta. Okay, it will let you write your equation in polar mode. But I want to go through that with you together in class, so we're not going to graph this together right now. Okay, the last example that we're going to do together today is converting from polar to rectangular. For this last example, we're actually going to do it in class together because I want to keep this video within the time limits I set for myself. So we will do this last problem together. If you wanted to give it a try as a challenge, you're more than welcome to, and we will look at this next class.